Alright, we're going to end up with acid and base neutralization to finish our acid and base unit. So we're going to take an acid with a extremely low pH, high H concentration, and mix it with a base with an extremely high OH concentration or a low pH. We're going to put them together and see what happens. Okay, so all neutralizations are essentially just double replacement reactions. So I want to show you really quick strong acid, strong base, and what they end up making. Okay, just for giggles, we're going to use HCl, which we all know is a strong acid. We're going to add that to NaOH, sodium hydroxide, okay, which is a strong base. We're going to put it together. It's a double replacement reaction, so we're going to keep our metals in the same spots on this side. So H, and then Na, and then we're going to switch the anions with them. So Cl is going to go to Na, and then OH is going to go to our H. So we end up with our products of HOH, which we know is water, and NaCl, which is a salt. Now remember, salts don't have to be NaCl, even though NaCl is, that's what we think of as salt. Okay, salt is just anything that is going to be the product of an acid-base reaction. Okay, so that's very, very important. Strong acid, strong base. This is what we end up with. We'll always end up with the water. We'll always end up with the salt. Now, depending if it's neutral or not, depends on how much we have. If we have equal parts of acid and base, we're going to end up with a neutral solution. Now, obviously, if we have more of one than the other, it's going to push it in that direction. Okay, that's where equivalence is a very important term that we're going to talk about. So equivalence, let's take a look at it. Yeah. Equivalents are important topics in chemistry because we're not dealing with just necessarily one H being produced or one OH being produced. We may be producing several of them, and when I make more of them, it's going to have a different effect than just the one. So the more we produce, the more active it can be. So HCl. If I have 1 molar HCl, it's going to put off an H positive ion. Okay. Now that H positive ion is going to be the same concentration as my original one. Okay, that's just a thing we know from just doing our basic chemistry from way back when we were talking about stoichiometry. Now H2SO4, which is our diprotic acid, though, when it produces an H, it produces more equivalents of H. Okay, so yeah, it's going to be the same molarity, but we're going to come up with a new term. Okay, we're going to add a new term to our concentration, and that new term is going to be called normality. Okay, so normality is going to be very beneficial to us when we're doing diprotics and we're doing triprotics, or we're doing bases that have more than one OH attached to it. So this, yes, it has the same molarity, but now it's got twice as many H's. So that means the H's do twice as much work on whatever it is that it's attacking. Whether since we're doing neutralization, it has twice the effect on the base. So instead of having a molarity of 1, that's not really, it's telling us what it does. It has a molarity or normality of 2 times because I have 2 equivalents of H. Okay, I have 2 times the amount of H here as I do in the original one. So normality is big because now I have 2 normal. So we use the big N to represent what I have here. So this is a 2 normal solution, even though, let's write there, this is a 1 molarity or 1 molar solution. So the equivalents tell us it's going to have a 2 normal. Okay, I'm going to erase normality. You still need that somewhere. So if I have the same thing, a 1 molar solution of H3PO4, okay, phosphoric acid. So phosphoric acid has 3 H's. Yes, it still produces off H, but the H's now, instead of making 1 times or 2 times, it's now 3 times as much, or 3 equivalents of H. So that would make it 3 normal. So our equivalence times our molarity, that will give us normality. Again, it's going to be very beneficial when we're doing neutralization equations. Okay, I can do the same thing with bases. So NaOH, okay, it puts off 1 OH. So it's the same. So anytime we deal with just the 1, and we have 1 OH being produced, that's easy. We don't even have to do anything. Okay, but let's say I have CuOH2. Okay, now I have 2 OHs being produced. Okay, so now I have to say I have 2 equivalents. 2 equivalents times our 1 molarity gives us 2 normal. Okay, let's say I have aluminum hydroxide. Aluminum hydroxide is AlOH3. Again, it's putting off OH negative, but now I'm putting off 3 units of it. And so those 3 units, or the 3 equivalents of it, times our molarity, would give us 3 normal. So normality is important when you have more than one thing. So if I have more than 1 OH or more than 1 H, I don't need to even worry about it if I'm just dealing with something that is equal equivalents on both sides. So if I have CuOH2 and H2SO4, it doesn't matter if I do normality or molarity, because both of them are going to offset each other. So that's an important thing, and we'll see some examples with that in the next couple days. Okay, titrations. Titrations are when we take an acid and a base and we make a battle. Okay, we want to get to an endpoint. The endpoints could be whatever we set. We're going to know we hit an endpoint though because we have what's called an indicator. Indicators could be something that changes at any pH. It could be a low pH, it could be a high pH. I just need to make sure that that pH is something that I'm looking for. So if I'm working in a pharmaceutical company, let's say that I need the drugs to react at a certain rate, at a certain pH, I may put an indicator in there to show when I hit that pH. So if I need it to be at a pH of less than 1, okay, there's some indicators that I can do that will show that I actually have that pH of less than 1. So indicators are pretty handy. They change colors. They're awesome. They're cool. Everybody likes them because they change colors and they're pretty. All right, the titration that you're going to be doing is going to be a titration of an acid and a base. It's going to be the HCl, which we made before in our solutions lab. It's back in the fume hood. And you're going to put that together with an unknown base. Okay, you're going to titrate the base with the known acid. That's called our standard solution because we know what it is. The standard solution is what we know. If you did a good job with your lab earlier, you're not going to have a problem. Everything's going to be beautiful. If you struggled with the lab before and you had a hard time with it, this lab might be ugly too, and it might be just showing its ugly head right about now. Okay, so what we're going to do is we're going to mix them together, and we're going to hit our equivalent points. Now, we're going to hit an equivalent point with what's called phenolphthalein. Phenolphthalein is going to be roughly about 8 when it changes colors. Phenolphthalein will change from a clear color to a pink color. So we're going to be looking for a really, really light pink so we know exactly when we get there. Now, it's not going to be exactly neutral, but it's going to be close enough for what we're doing. So the titration equation, I want to show a couple of them real quick for you, is MaVa equals MbVb, which should look pretty similar because this is basically just our dilution equation. Okay, we're going to put the molarity of the acid against the molarity of the base and let them go after each other. Okay, if I have a strong molar one and a weak molar, obviously I'm going to need a lot more of the weak molar to offset the strong acid. Okay, now that works great if your equivalents are the same for your acid and your base. Okay, so if I have HCl and NaOH, that works awesome. Okay, it doesn't work so awesome if you have HCl and CuOH2. Okay, because my equivalents are off. If your equivalents are off, you're going to want to use your normality instead. So NaVa equals NbVb. Okay, so that's going to be the equation you're going to need to actually solve for your unknown solution on, well, probably sometime at the end of this week. So make sure you have this down because you are definitely going to need that equation. All right, now we have buffers. Buffers are essentially salts of weak acids and weak bases. What they do is they basically act like pH sinks. If I add hydrogen into them, they absorb all the hydrogen, so they prevent the hydrogen from going out and doing hydrogen things and being acidy. I don't even know how I'm going to say that, but it sounds awesome. It's going to hold them back. It's going to put them into their little pouch and keep them there. So what we have here is we have sodium ethanoate, which is a fun word to say, but the sodium ethanoate breaks down into these two bits right here. We don't even worry about what they're called right now. But what we have here is we're going to add this to an acid. So here's our buffer. So if I have a buffer and I add H to this, it is going to go away, Titus. It is going to be sucked into this. Okay? So I am going to absorb it here, and we are going to make what is called ethanoic acid. All right. Now, ethanoic acid is a weak acid. It's got a low Ka. If it's got a low Ka, the H isn't getting out. It's not dissociated. It's not breaking out into smaller little pieces and going out and causing havoc. Okay, so the pH will change, but the pH will only change a little bit. Now, there's a thing that's called a buffer capacity, because eventually, what happens when I keep on adding H to this? I keep adding H. I keep adding H, and eventually I run out and I can't add anymore. Tell them to go away. So, eventually I'm going to have to stop. And once I hit that point to where I stop, eventually this is all gone, and what are you left with? A bunch of H. Okay, once I hit that point to where all the H is now pouring into the system, now I have what's called buffer capacity, and we have hit that point, and things get kind of ugly. All right, now that happens both with acids and bases. I could show you what happens with the base as well. When we add the base, the same thing happens. It gets absorbed into there. So buffers work for both acids and bases. They take them both in, and acids are our buffers. So when you eat a Tums, okay, it's not just like dropping base into your stomach. It's a buffer. It absorbs the acid in your stomach. All right, guys, have a great evening. We'll see you later.